Let's take a look at our next problem. So we're given a cylindrical wire carrying a current, and we know whenever a wire carries a current that it generates a magnetic field. This time we're asked to find the magnitude and direction of the magnetic field at a point inside the radius of the wire. So the first thing we need to do is use Ampere's law to find an expression for the magnetic field. So here's our wire. We're going to draw a circular Amperian loop around it. One little infinitesimally small bit of this loop S we'll call ds, and that is in fact a vector. It has a direction at each point. So we can rewrite b dot ds as b ds cosine theta, where theta is, as usual, the angle between b and ds. So if we look at the wire on end and consider the magnetic field at a distance r away from it, the Biot-Savart law tells us that that B field is 90 degrees away from r, which means that at each point along this circle, B lies in the same direction as S. That means that the angle between them is 0 and the cosine is 1. Furthermore, we can notice that since the entire loop S is 2 pi times r for this radius away r, that means ds is 2 pi dr. And we can substitute this in for ds. And that gives us 2 pi times b times dr. Notice that b is a constant with respect to s because since we've chosen this as a circle, the radius r away is the same at every point. That means that the B field is going to be equal at all points. The magnitude, rather, of the B field is going to be equal at all points along this loop. And since B is a constant with respect to S, we can pull B outside whenever we integrate. The integral then becomes 2 pi B times the integral of dr, and that is simply 2 pi r times b. This is hardly surprising because 2 pi r is the length of S, and that's just multiplied by the magnitude of the B field. It's very analogous to whenever we worked out Gauss's law over the sphere and got the surface area of the sphere times the E field. Now we have an expression for the left-hand side of Ampere's law. What about the right-hand side? We don't actually know how much current is being enclosed yet. If we were considering a point outside of the wire, it would be the entire current of the wire, but we're considering a point on the inside. So if we look at the cross-sectional area of the wire, we'll say that the wire has radius capital R, and that the area that we're considering has radius lowercase r. It may not be immediately obvious at first, but the problem told us that we have a uniform current density, which means that there's no more current at this spot here, than here, than here, than here, for example. The current density is the same throughout the cross-sectional area of the wire. And that means the ratio of the current enclosed by this Amperian loop to the total current is going to be equal to the ratio of these two areas. And again, this may not be immediately obvious at first, but it follows directly from the fact that the current density is uniform throughout. And then solving for the enclosed current, obviously these two pi's are going to cancel. We get the ratio of the squared radii times the total current. We've now accounted for both sides of Ampere's law, and we can now equate these two expressions and solve for B. So 2 pi r b is equal to mu naught times I enclosed, which is this expression, r squared over capital R squared times the total current. This means that the magnitude of the B field is given by mu naught R squared times the current, total current, upon 2 pi R capital R squared. Lowercase r will cancel, and we're left with mu naught R total current upon 2 pi uppercase R squared. Using a calculator, I got 6.4 times 10 to the minus fifth. This is a B field, so the units should come out in Tesla, and let's check to make sure the units actually do come out properly. So here we have amps in the denominator, canceling with amps in the numerator. This is meters squared, so we have meters canceling here and here with those, and we're left just with Tesla. So the units do work out.